Hello, I'm Dr. Tydell. We've already met because you've probably watched 3 videos. If you haven't already watched 3 videos, you're missing a lot. There's a video that introduces me and the lab. There's a video that introduces how to navigate the Canvas page for the lab. And there's a video about how to run Proctorio. So go back and have a look at those. They are available on the Canvas page. But now let's get going. Let's talk about the scientific method. How do scientists figure things out? By the way, scientific method doesn't seem like an invention. When I describe it, you're going to say to yourself, yeah, of course. How else would you figure things out and prove that that's the truth? But it actually was a discovery, and it didn't happen until like the Age of Enlightenment, somewhere in Europe anyway. It didn't happen until then. So let's start with some definitions. You need to know the difference between a scientific hypothesis, a scientific theory, and a scientific law, all right? The words hypothesis, theory, and law, these guys are also just used in common speech, right? On a cop show, they might say, my theory of how the murder was committed is X, Y, or Z, right? I'm not saying that's a wrong way to use the word, but I am saying that you need to know what do scientists mean when they say the word. So let's look at these definitions. Number 1, a hypothesis. A hypothesis is a proposed and testable explanation for the reason of a natural phenomenon, okay? The reason, not just what happens, but why it happens, okay? A hypothesis has to be testable. So if you told me that your hypothesis was that magical, invisible gremlins were moving things around, and I say, okay, let's put together an experiment. You'd say, oh no, you can't ever see or find these gremlins. Then I'd say, well, then that's not a hypothesis, okay? A hypothesis has to be testable. We have to be able to put together an experiment, at least theoretically, that we could test it, right? And it's always the explanation for why something happens. We'll get back to that in a moment. What's the difference between a hypothesis and a theory? Well, a hypothesis is just a testable explanation. It needs to be consistent with what has already been proven, but you don't need to have proven something yet to consider it a hypothesis. But a theory is a well-substantiated explanation of the reason for a natural phenomenon. Well-substantiated means that many scientists at many different universities and research labs have performed many experiments to test this explanation for why something has happened. And every time they've tested this particular explanation, they always come up with the same answer. Now you got yourself a theory, right? But what's a scientific law? First of all, let me tell you this because it's on the first quiz, which you're going to be taking next week. Theories never become laws. They're just two different things, okay? A scientific theory is an explanation of why something happens. A law, it's often a mathematical model just for predicting the phenomenon. For example, we have got the laws of thermodynamics. With the laws of thermodynamics, we can measure heat and heat energy and how much heat we expect to be produced by combustion of a certain volume of fuel, right? That's the basis for a law. We've got a law of gravity. With the law of gravity, if you tell me how big your planet is, I can tell you how much energy it will take to propel a rocket ship into orbit around the planet, okay? That's a law. Now, even though we have got a good law of gravity, we actually don't have a perfect theory of gravity yet, right? So laws and theories, two different things. Let's look a little more. A theory requires extensive experimentation under many different conditions. Lots of scientists need to perform lots of experiments to try and to substantiate that the reason why you think gravity happens, that's why gravity is happening, okay? But laws don't have to be tested at all. When Newton came up with the law of gravity, he just had to say, look, every time I measure it, I take these factors. This is a mathematical formula. Boom, done. No need to test it. Okay? Theories may become obsolete with time, usually not exactly get discarded because it's really hard to become a theory. Usually theories just need to get modified if something happens. Laws never become obsolete over time. So, law of gravity, I gave you that example. Newton, who came up with the law of gravity, he had no idea why gravity happened. Why is it that large masses like planets will pull objects like us towards them? Why? He had no idea why. Came up with a law. He can calculate it, but he didn't know why. An example of a theory is the theory of relativity or the theory of evolution. Those are why something is happening. And even though the theory of relativity and the theory of evolution are been tested so many, literally millions of times, that we feel like they are fact, they'll never become a law. Okay? So with the theory of relativity and the theory of evolution, so many experiments have been done that it's more than 99.9999% likely to be true, but it's never 100%. So scientists will always continue to test those theories. If even one experiment consistently causes us to reject something about that theory, we're going to have to at least modify it. But scientific law doesn't say why, it just says like how much. So the theory of relativity, this guy, Albert Einstein, came up with the theory of relativity in 1905. It's E equals mc squared, the equivalence of matter and energy. It wasn't actually definitively proven until 1917, right here at Mount Wilson, which is adjacent to the city of Pasadena. That's where the theory of relativity was first proven. And we test the theory of relativity every time you use the GPS on your phone. It's been tested millions of times. It will never be called the law of relativity, ever. It will always be the theory of relativity. So there, okay. Now, a guy named Niels Bohr, he actually came up with an experiment that actually caused the theory of relativity to be modified and generated this whole branch of physics called quantum physics. So we will continue to test it, and maybe it will get modified again. All right? Okay. Now, let's talk about steps in the scientific method. Steps in the scientific method. Step one, we notice something. Darwin noticed that the birds on this one island were similar to each other and yet also distinct species that didn't interbreed with each other. That's an observation. Newton noticed that things would fall to the ground and that they picked up speed as they fell, right? These were observations. You start with that and you say to yourself, why? Plants that grow in shade grow more slowly than those that grow in sunlight, depending on the plant, right? Why, right? Then you ask that question, why is that happening? And you come up with a hypothesis for why it's happening. Now, the hypothesis has to be, does it say here? The hypothesis has to be testable, okay? You can't say it's because of magic beans in the ground, No, it has to be testable. If you want to say the reason why plants grow better here than there is because they get more water, you can say, okay, I'm going to put together an experiment. I'm going to grow plants just like that in my greenhouse with the same light, give one more water, one less water, and I'm going to test and see if my hypothesis is true. Okay. Then I put together an experiment like that one. If I think that more water makes things grow better, I will plant, 1,000 identical little plants, and I will give them all the same light, exactly the same soil, exactly the same temperature, and I will give them different amounts of water every day and measure how quickly they grow. That'll be my experiment. I don't just have to set up an experiment and do the experiment, I have to collect the data, right? I have to go, okay, at the end of 2 weeks, these plants started out this high, and now they're this high with this many leaves, and the plants with more water are this high with this many leaves, right? I have to collect the data. Then I have to decide, was I right or was I wrong? Now, being right or being wrong, scientists don't say it that way. We say, should the hypothesis be accepted by this experiment or rejected? So it could be that in my experiment, I noticed that plants that got very little water, they didn't grow well at all. And as they got more water, they grew better. But then when they got too much water, they didn't grow well either. Okay, that would be my data collection. And at my conclusion, I would say, it seems that my hypothesis was kind of correct. Plants did grow better with more water, but only up to a point. Now I need to refine my hypothesis that there is an optimal amount of water for this breed of plant. Then I might try using that amount of water on different kinds of plants. And I'll retest it. I'll say, okay, maybe that is only true in fall. Maybe in winter it is different, right? Also, one thing, and I should put it here, and I will add it here right now. One more thing is you need to communicate it. Scientists do not consider science, the scientific method, to be properly followed if it is not communicated, right? Scientists are really big on this. If a scientist says, I did research and I have come up with a cure for the coronavirus, here, take this pill, scientists are going, no, you're not a scientist because you had not communicated how you did the experiment and what your data was and what is in that pill, right? In order for something to actually be following the scientific method, all of that needs to be communicated. Now, if you're developing a cure for coronavirus and you're working for a fancy pharmaceutical company, you don't publish the data until after you get the rights to sell that medication just yourself. But ultimately, you've got to communicate it. Okay. So, observations, scientists notice something in the natural world, like plants in a shady spot in a field grow more slowly than plants in a sunny spot. And then we come up with a hypothesis. That's a suggested explanation for the observed phenomenon, right? And this one might be, oh, remember, it has to be testable. So when we say it's testable, hypotheses are often written as an if-then statement. So if I provide more sunlight for my plants, then they will grow faster. That could be my hypothesis. And it predicts an outcome. So it predicts what will happen in my experiment. If I give them more light, then they will grow faster, assuming the same amount of water and temperature. Now, hypotheses do not have to be perfect. They don't even have to be correct. All right. If I came up with a hypothesis that plants grow better when they get, what was this? When they get less sun, if I predicted that they would grow faster if they got less sun, and I put together an experiment, well, I would have proven my hypothesis was false. I would have had a group of data that would have rejected my hypothesis. Does that mean I'm a bad scientist? No. It means my hypothesis was incorrect. I need to put together a new hypothesis, right? So your hypothesis, as long as it's testable, you don't have to have guessed the right answer. Your experiment will tell you this was not a correct hypothesis or not an entirely complete hypothesis, right? And then you will go on from there, okay? So, can you create a hypothesis for why the observed plants grow more quickly in a sunny spot rather than a shady spot? So let's try that. We could say, more shade keeps the soil too wet for plants to grow well. In that case, in our greenhouse, instead of using more light and less light, we would have some situations where the soil stayed wet and some where the soil stayed dry and kept them at the same amount of light. That would have been our hypothesis, right? Or we could have had a hypothesis that the soil in the sunny area has more nutrients, and it's more nutrients that let the plant grow faster. Great. Then we would come up with the hypothesis that plants grow better with more nutrients. And then we would have had to prove that when I take soil from the sunny areas, I find more nutrients in that soil. That would have been my experiment. Or I could have said more light provides the energy that allows plants to grow. So then in my greenhouse, I would have exactly the same soil, exactly the same plants, exactly the same amount of water every day, but different amount, exactly the same temperature, but different amount of light every day, okay? We will pick up here at the beginning of the next video.